Right, and for this last surface in question number 10, we're going to look at surface number 4, described by the equation x squared over 4 plus y squared over 9 is equal to z squared. This is what's known as an elliptic cone. All right, so we can start out by looking at the y-z traces, where you set x equal to a constant. We get the equation c squared over 4 plus y squared over 9 is equal to z squared. So if you subtract y squared over 9 from both sides and rearrange, we get this equation, z squared minus y squared over 9 is equal to c squared over 4. And notice here, this expression on the left, because of this difference, can actually take on positive and negative values. So I'm not placing a restriction on c like I've done with some of these other examples. Okay, now if c is non-zero, I can go ahead and divide both sides of this equation by c squared over 4, and I recognize this equation as the equation of a hyperbola. Okay, so in the special case when c is equal to 0, okay, if I go back up to this equation, I find that z squared minus y squared over 9 is equal to 0. Okay, so in other words, z is equal to plus or minus y over 3. So that's saying that our surface will intersect the yz plane in this pair of lines through the origin, described by z is equal to either y over 3 or negative y over 3. All right. For all other values of c, again, we get a family of hyperbolas described by this equation. Okay, so for example, if c is either 1 or negative 1, okay, due to this square here on the c, okay, we're going to get the hyperbola whose top branch is right here and whose bottom branch is right here. If c is plus or minus 2, we're going to get the hyperbola whose top branch is here and whose bottom branch is here, so on and so forth. All right, great. So now let's move on and look at the xz traces. So we set y equal to a constant, and we get x squared over 4 plus c squared over 9 is equal to z squared. So subtract x squared over 4 from both sides and rearrange. So we get z squared minus x squared over 4 is equal to c squared over 9. And again, if c is non-zero, I can divide both sides of this equation by c squared over 9, and I get this here, which I recognize as the equation of a hyperbola. Okay, so what if c is equal to 0? Well, going back up here, I get that z squared minus x squared over 4 is equal to 0, which implies that z is equal to plus or minus x over 2. So that's telling us that the intersection of our surface with the xz plane is this pair of lines here, described by the equation z is equal to either x over 2 or negative x over 2. Okay, great. So we have, right, these pair of lines for the origin, right, for the intersection of our surface with the yz plane, and then hyperbolas for planes parallel to the yz plane. And then when we intersect our surface with the xz plane, again, a pair of lines. And then for planes parallel to the xz plane, we get hyperbolas. And then for our xy traces, okay, so looking at the intersection of our surface with planes parallel to the xy plane. Well, setting z equal to c, I get x squared over 4 plus y squared over 9 is equal to c squared. And if I divide both sides of this equation by c squared, as long as c is not 0, that's okay, I get this equation, right? This is the equation of an ellipse. Okay, now in the case when c is 0, okay, that's just going to give us what? Well, x squared over 4 plus y squared over 9 is equal to 0. That is true only when both x and y are 0. So here, the intersection of our surface with the xy plane is in fact a single point. Okay, it's just the origin here in the xy plane. And for all other cross sections, right, we're going to get ellipses here. All right, so now we're going to put all of that together. What are we going to get? Well, we're going to get a cone, okay, where the cross sections are these ellipses here, hence the name elliptic cone. And, right, coming back to parts A and B, we see that the intersection of this cone with the YZ plane, right? That's going to be this pair of lines here. So, sorry, here and here. If we look at the intersection of our cone with the XZ plane, right? That's going to be these lines here. And now, if I say, look at the intersection of our cone with the plane, say x equals 1. Okay, so we know up here we're going to get a hyperbola. Well, that's going to be what? It's going to be this curve up here that lies on the intersection of the plane x equals 1 and our cone. That's the top branch, right? That's corresponding to this top branch up here. But then we're going to get this symmetric bottom branch down here on the lower portion of the cone. And you can see, right, if you let x vary, right, you're going to get this whole family of hyperbolas. And likewise, if you cut the surface with planes parallel to the xz plane, okay, you're going to get this family of hyperbolas, except in the xz plane itself, where you get that pair of lines. All right, great. Well, that does it for this video and for question 10. Thanks so much.